Hi guys, so today we are going to look at, we're going to finish up our kinetics of rigid bodies. The theory, we've almost pretty much gone through everything, just a little bit to go through, but today we'll focus more on problems. So this lecture is going to be super short, so let's get right. So we were looking at the general equations of motion for planar motion, right? All right, and what we had essentially looked at last week was that, let's say we have a rigid body like that, so that's for the free body diagram, and then that's for the kinetic diagram. So you have a bunch of different forces which are acting on it, right? Let's say F1, F2, F3, and F4. And then maybe you have some moments that are also acting on it. So let's say that you have 1, M2, right? And then there's a random point P that we're interested in looking at. So call that guy point P. And then when you're looking at the equivalent kinetic motion, so this is the free body diagram, right? So that's the FBD. That defines all the forces and the moments that are acting on the body. So this is equivalent to the kinetic diagram, which we had seen that in our XY coordinate system, that about, so let's define center point, so the mass center, so G, so you have an equivalent acceleration in the x direction and you have an equivalent acceleration in the y direction, and you've got an equivalent rotational motion, so that is IG alpha, right? And again, we're looking at this random point P on it, and let's say that the perpendicular distance of P from the vertical about which passes through the point G is equal to dx, and the horizontal distance and the vertical distance of the point P from the horizontal axis, let's say that is equal to dy, right? And we'd seen that the equations of motion for this problem are going to be equal for this situation are that the sum of forces in the x direction from your free body diagram is equal to mass times the equivalent acceleration in the x direction. Then you have it in the y direction as well. So this ends up this gives you two expressions, right? And then you can get a third expression by looking at the moments, and the moments can be looked about any random point. So that random point we decided for our intents and purposes was point P. So summing the moments about the point P. So from the free body diagram, that is equal to the sum of the moments that are applied. So that's, let's call that sigma m. And plus you have the moments of the forces that are applied about the point P, right? So add all those moments up. So the moments due to all the forces F about the point P. So this is all from the free body diagram. And that, so let's say that this expression in the kinetic diagram is equal to, now again, remember we're about the point P, right? So you'll always have your IG alpha equivalent motion, right? But now you also have the moments due to these equivalent motion forces, so MA alpha, right? So you have plus MA G. So now G going positive, so that's positive. So So MAGX is going to be positive and MAGY is going to be negative. So MAGX times dy minus M of AGY times dx, right? Or it's more convenient to look at the moment about the mass center G, right? And that guy is equal to, again, from the free body diagram, the sum of all the moments that are applied plus the moments of the forces that are applied about the point G. So all the forces, the moments about all the moments about the forces about the point G. And what's that equal to? Now you're taking moments here about the point G. So MAGY and MAGX pass through that point. So those terms are not there. So this is just simply equal to IG alpha. So these end up giving you three expressions for your forces and your moments. And this is true for any kind of planar motion for rigid bodies. Now, a specific kind of planar motion, let me get rid of these expressions here. A specific kind is when a rigid body is rotating about a fixed point, and that's what's called constrained motion. Right? So what's happening now is, let's get rid of everything. So now I've got, let's say, I've got my body like that, right? So we're going to do it for the free body diagram and for the kinetic diagram as well. But what's happening is at this point is rotating about a fixed point, so it's pinned like that, right? And what that ends up, so let's call that point O. Okay, like that. And what that ends up creating is, because there's rotation happening in my kinetic diagram, I can say that there is going to be an angular velocity and an angular acceleration. And I'm keeping these guys positive. All right? Okay, so now when I'm looking at the free body diagram and the kinetic diagram, what's going on? So now looking at the free body diagram, I have all of my external forces, right? So F1, 2, 3, and 4, right? Let's define all the points that we have. So you've got the mass center, always going to call that G. You have a random point P that you're always working with, because it kind of makes sense, because sometimes you might need to use that point, right? And you have the point O over there, right? So let's draw the point in the kinetic diagram too. So you have G and you've got the point P like that, right? Okay, so now when I'm looking at the free body diagram, I've got all my forces, right? I have got my external moments, say M1 and M2, right? And to complete the problem, what's the big force that I'm missing? So now, considering that we're looking at this in the XY frame and you have the weight acting, so let's just say that for completeness sake, you might have the weight of the rigid body that's going to act at the mass center G, right? But I'm still missing some forces here, right? Because when you have a pin about which rotation is happening, you are going to have pin reaction forces. So you will have a resultant, the direction of which will be unknown. So you will have a reaction force at a pin. And remember, when you're solving problems, this is usually always going to be an unknown. All right? Now, the interesting thing about this is that you could look at this in your XY coordinate system and try to solve, but that often complicates things, right? An easier way to look at this is basically to say that, look, there's rotation that's happening about this point O, right? So if I look at the point G, or any point on this, but let's look at the point G, what kind of path is it going to trace about the point O? a circle, right? Because it's rotating about that point, right? So then I can draw my normal and tangential frame of reference, which we see is going to make life easy. So I'm going to have, let's say that you have the normal and your tangential directions over there, right? So what does that allow me to do? That allows me that when I'm looking at my kinetic diagram, so again FBD and KD, and I'm looking at the point G, right? So I can have, so M, A, G, N like that, and then a tangential term, which is M, A, G, T like that, right? And then I still have my IG alpha term, which is resulting from the rotation, right? So let's say you have IG alpha like that over there, right? And then just to complete it, because we see it's going to come into the picture anyways, draw the normal direction and your tangential direction. Let's define the two distances. So let's call this perpendicular distance dt. Let's call that perpendicular distance dn, like that. All right? So now I've got rotation which is happening, and I've defined this new coordinate system, which we see. I know it's like kind of setting it up without telling you guys what the payoff is going to be, but it's basically going to make our lives easier when you're looking at rotation about a fixed point, right? Why does it make it easier? Because you're looking at rotation about a fixed axis. Through this point O in our case, right? So you can say that the sum of forces in the normal direction, so summing all these forces in the normal direction, including your reaction forces, that's what's going to be coming into this side over here. That is equal to the equivalent motion mass times the acceleration in the normal direction, right? And similarly, you can say that F of t in your tangential direction, you sum all these forces in the tangential direction, that's equal to mass times your equivalent motion in the tangential direction. Now, what's the point of doing this? Ashish, you're driving us crazy with all this math. No, there's a point to this. The reason you do this is for rotation, you can get what AGN and AGT are equal to in terms of omega and alpha. Remember, right? Because the acceleration in the tangential direction is just equal to omega, the vector omega crossed with r, and in the normal direction is just the vector omega crossed with r. Remember, that's your omega crossed with r. Remember, that's your centrifugal acceleration term. And then you've got the alpha r acceleration term, so that's alpha crossed with r. That gives you the acceleration in the tangential direction. And when we're looking at planar problems, you can simplify the math to simply say that, now, like, if this distance, define that to be rg like that, you can say that a of g, the scalar terms, right, not the vector terms. Although you can do the vector math too, but you guys know this, that you can write the scalar terms. So the normal acceleration is just that omega crossed with r, but if you look at the scalar term in planar motion, that's just going to be equal to omega squared times this distance rg, like that. And then acceleration in the tangential direction is going to equal what? It's alpha, the vector alpha crossed with rg. So if you write that out, the scalar term is just equal to alpha rg, like that. And that's the reason for looking at this tangential and normal direction, because then you can get your terms for your acceleration easily, right? And now the only thing that's left is to get the third equation for the moment. And again, you can do it about any point. So let's do it about a general point, P, right? As always, MP is equal to the sum of all the moments that are acting, right, plus the sum of moments due to all the forces that are acting on it about the point P, like that, right? And what's that going to equal? That equals my Ig alpha term in the kinetic diagram, right? Plus, now, about the point P, I'm going to have to take components of both MAG tangential and MAG normal, right? That's why I drew out these dx and dn terms, right? So for my AGN, it's going to be positive, and AGT, it's going to be negative. So plus I'm going to run out of space over here. MFF cross with P is equal to Ig alpha plus MAGN is positive, so M crossed with MAGN crossed with dx Well, I should have said it's dt, not dx. So times dt, like that, minus MAGT times dn, right? So that's one way that you can get your moment term equations, all right? But it's not, you have to do a lot of work because you have to find out what these two additional terms are. Or, but we know, you can also do it about the point G, right? So if you find the moments above the point G, you just see you're summing from your free body diagram, you're just summing all the external moments plus the moments due to all the external forces about the point G. And what's that equal to? That's just equal to Ig alpha, right? Because now you're taking in your kinetic diagram, you're taking moments about the point G. Both this MAGT and MAGN pass through that point, so it doesn't matter. So they don't show up on the right hand side over here. All right? Or, and this is the interesting thing, you can take the moments about the point O, right? And this is where the fun happens. So about the point O, again, from the free body diagram, you have the sum of all the moments plus you have the sum of the moments due to all the forces about the point O. And that is going to equal, always have your Ig alpha term, but now you're taking the moments of this equivalent motion. This MAGN is passing through the point O, so it doesn't matter, that term goes away. But you are going to have a positive MAGT term due to this, with this distance RG, right? So what does that equal? That's plus MAGT times your distance RG, right? Now what is MAGT equal to? So Ig alpha plus. We had seen that AGT is equal to alpha RG, right? So you have M times, you end up with alpha, M alpha times RG squared. And here, if I take alpha out, now remember the angular acceleration for this rigid body is about the point O. So this alpha in this Ig alpha term and this alpha that I'm using in this expression is the same, right? So I can just take that alpha out, and that gives me alpha times Ig plus M RG squared. You guys know where I'm going with this, right? What is this equal to? From my parallel axis theorem, this term is just equal to the mass moment of inertia above the point O. So from my kinetic diagram, my kinetic motion, if I'm taking moments above the point O, that's just equal to IO alpha. And sometimes that's very helpful because when you're looking at the left-hand side terms, you can get rid of the reaction unknown forces, and that kind of helps with our math. But if you're using Mathematica or a computational tool, it doesn't really matter how you define how you get the third equation. All right? Okay, so with that, we see that when you're having this constrained motion with rotations happening about a point, fixed point, and it's not moving, you can get your three equations of motion this way. All right? Thanks.